Amazing, what a star-studded panel. And now we are on to our final session of the event. It's time to sit back, relax, and hear from the young minds and the great CDR solutions that they're developing and inventing. So very pleased to hand over to Sue from OpenAir to run the show. Welcome.
Oh, thank you. Thank you, everyone, and thanks for the shout out to Gigaton Bio earlier. That is one of our teams that will be presenting last but not least today. So I'm Sue Dorward. I'm the lead of the Carbon Removal Challenge from the OpenAir Collective. The OpenAir Collective is a grassroots volunteer organization. We are affiliated with a nonprofit, and we are mostly known for policy work, but we also do a lot in the innovation space. So the co-founders were Chris Neidl, who many of you are familiar with. He moderated a panel yesterday. And Matt Parker over here, who's manning the awards for the students. Matt is the co-founder, and he started the Carbon Removal Challenge 4 years ago. This is our 4th year. And it just keeps getting better every year. So today, I'm going to do a brief intro, and then we're going to go through the 4 winning student team presentations. In the interest of time, we're not going to have a Q&A with each of the teams. You can get them after the event. This is the last event of the day, so you can run over and grab them, and you're not interfering with anything. So let's dive in here quickly. First off, I want to thank our sponsors. We had a couple of very generous anonymous donors, one at the gold level, one at the bronze level. We also had other online donors to our crowdfunding campaign, so thank you very much to you all. We also have 1.5 TerraSet and Carbon Business Council as bronze level sponsors. Carbon Unbound, of course, we're grateful to them as our venue sponsor and for sponsoring the student spots at the conference the past couple days. And also we have in-kind sponsorships from Possible Studio, B3 Carbon, and Carbon Manager LLC. So what is the challenge? It is a global college and university student competition in which we support students in designing and creating greenhouse gas removal and carbon dioxide removal solutions. We kicked it off way back in September along with Climate Week. We've been doing monthly webinars with experts in the field since then, and had a mentoring program as well. The student applications were due in March, and we had 24 expert judges, also volunteers to help us choose the winners. So thank you to those of you who are here who were judges. Much appreciated that you were willing to spend your time and lend your expertise for our program. And so then we announced the winners in April, and now here we are in May with the students presenting their solutions. So I mentioned that we had a webinar series. Tonight will be our 8th webinar as we'll broadcast these presentations. And you'll see some familiar faces among our panelists. If you go to our website, you can get links to the recordings of all of our webinars. And of course, who can do a webinar series in CDR without Tito Jankowski? Shout out to him for his great support. And so he brought in a couple of startups for one of our webinars. We had a big buyers webinar with Lindsay from TerraSet moderating. We had folks from Ren and Carbon Direct and Shopify and Milky Wire. So we're getting the big names here supporting our student program. And then our most recent webinar, we even had Ollie from Unbound as one of our panelists, along with Ben Rubin from Carbon Business Council and Joanna from Frontier. So thank you, all of you who have participated in one way or another in our program. So this year we had 37 teams apply, and you can see the stats here, and it's a global program, and we selected 4 winning teams. We also selected 4 honorable mentions. We had some really high-quality submissions from Jiangsu University in China, University of Waterloo, which was a winner last year, from Canada, IIT, and the University of Maryland. And our winners this year are from Rutgers. They have a carbon capture with concrete waste solution, and where they extract the cement from waste concrete and carbonate it. We have KAIST that came all the way from Korea. Their MMML carbon removal team worked on a very efficient manufacturing of a solvent-free process for creating sorbents, and also a sorbent design along with that. We have the Michigan Carbon Capture's Project Sapphire. They were a runner-up last year, so they came in and won this year. They are using microbes in a wastewater system and also generating and capturing hydrogen. And then last but not least, it's our Gigaton Bio team, which is from Cornell, Princeton, and Columbia. And they are doing genetic engineering of bacteria to mineralize CO2 and also extract critical metals. So with that, I want to kick it off with our team presentations with Rutgers C3W. Please come up on the stage. And the microphones are in the chair.
Hi everyone, we're C3W and we focus on carbon capture using concrete waste. My name is Noemie, these are my teammates. We are part of the material science and engineering and civil and environmental engineering departments at Rutgers University under the PIs Dr. Richard Ryman and Dr. Yalin Lee. We're two research groups that collaborate often, and our research focuses are on the development of next generation materials for sustainable construction and the sustainable design, cost, and environmental analyses for early stage technologies.
Our approach relies on CO2 mineralization, which is exemplified by this reaction over here. CO2 mineralization is routinely used in DAC plants. So it has been validated at scale. However, it is expensive and it is energy intensive to produce that sorbent. So to unleash the full potential of mineralization, we need a cheap, abundant sorbent feedstock. Our target feedstock is hydrated Portland cement. That's the binder in concrete. Now, hydrated Portland cement is rich in carbon capturing phases. Unfortunately, although it is abundant, the US generates 70 million tons of disposed cement every year. The problem is that it is trapped in waste concrete. We need to separate the cement from the aggregate phases before it can be used for DAC. Our group is collaborating with an industrial partner to apply a novel waste separation technique to the waste cement. This will liberate the cement for carbon capture. This is going to enable permanent CO2 sequestration in a verifiable, scalable, profitable way.
That's where our proprietary separation process comes in. It separates waste concrete into two products. First is the high purity hydrated Portland cement slurry that is ready to be used as a CO2 sorbent. And second is a clean aggregate that we can sell and ready to use for new concrete. So the maximum CO2 uptake of hydrated Portland cement is 430 kilograms of CO2 per ton of concrete. In our lab scale experiments, we have been able to achieve 210 kilograms of CO2 uptake in less than 2 weeks under atmospheric pressure, room temperature, without any chemical additives. That is a remarkable result and can be further optimized by improving sorbent air contact. So now that we understand how C3W works, let's talk about how it scales. First, waste concrete is collected in containers set at construction and demolition sites. They're picked up by roll-off dumpster trucks, which integrates us into existing waste management infrastructure. It also gives us an advantage over the standard CO2 mineralization methods because we're not limited to the mineral deposit mines and can operate anywhere where our feedstock is available. After it makes it to our our processing plants, we use our proprietary separation process to extract the hydrated Portland cement slurry. The collaborator we're working with to scale this have already used the process at 10 ton per hour scale with other feedstock materials. Finally, the slurry gets spread out in thin layers on stackable metal trays. This allows us to maximize the sorbent air contact, minimize the land use, and has also been verified by other ventures to work at scale.
So now we'll talk a little bit about how much this all costs. We made 2 different cost estimates for 2 different scenarios. In our first scenario, our upper bound scenario, we assume that we've done a great job optimizing our technology and that the process is operating as efficiently as possible. And in our lower bound scenario, we assume that we make no improvements beyond the initial lab scale performance. So we'll look at the costs first, and based on our analyses, you can see that C3W costs about $10 per ton of waste concrete processed, including both capital and operating expenditures. Now, when we add revenue due to the tipping fees and the sale of recovered aggregates to that, we can see that C3W can operate not just cheaply, but profitably at scale, generating over $20 per ton of waste concrete. Now, this is pretty remarkable, and it distinguishes C3W from other technologies in its field, because as far as we know, there are currently no direct air capture methods, especially mineralization methods, on the market currently that can make a profit. So in summary, we have a CO2 mineralization strategy that uses a feedstock with worldwide availability, available anywhere concrete waste or concrete infrastructure is used, uses simple, scalable equipment for all of its processing, and most importantly, can operate profitably. Now, there are some limitations, and the main limitation centers around our use of diesel-powered trucks for waste transportation. Of course, diesel is expensive and emits CO2 when you burn it. You can see in our estimates here that the use of diesel fuel increases our costs and decreases our net CO2 removal. You can see the numbers there for 2 different average transportation distances. And the net result of all this is that C3W really is most suitable for use in urban or suburban areas, areas with a high density of waste concrete production, so you don't have to transport it very far. Now, despite this limitation, we estimate that in the US alone, if scaled, C3W could sequester up to 17 million tons of CO2 annually and up to 83 million tons annually across the globe.
So like Jack mentioned, transportation has a significant effect on our net revenue and the net CO2 sequestered in our process. We estimate that with the use of electric trucks, we can significantly reduce the CO2 emissions associated with transportation for a small additional cost per ton of CO2 sequestered. Additionally, the presentation of our venture today does not include potential collaborations that we can have with existing waste collection and processing facilities. However, by leveraging this existing infrastructure and deploying modular separation and carbon capture units, we can effectively write off transportation out of our process altogether. Today, we focused on waste cement and waste concrete being used for carbon capture. However, the products that we produce in our process are quite versatile. First, the separated cement can be used for ocean alkalinity enhancement and soil amendment because its chemistry is actually pretty similar to the natural alkaline minerals already used in this space. The carbonated cement output can be used as filler or supplementary cementitious material in the making of new cement because of its high amorphous silica content. this carbonated output can also be used as a partial cement kiln replacement in the making of new cement, thereby closing the loop in cement production. So where do we go from here? We have already started the patenting process, and we aim to finish that in the next year. We're also looking to secure funding so that we can continue our lab-scale optimization. After lab-scale development, we would like to create a startup venture so that we can rapidly scale this technology. And within 5 years, we would like to develop or to deploy this technology to the market as a highly profitable, highly impactful carbon capture method. For this reason, we are looking for collaboration and funding opportunities that will help us bridge the gap between our preliminary results and a patentable, startup-ready technology. Finally, we would like to thank Carbon Unbound and the OpenAir Collective for the opportunity to present our work, the CRC Organizing Committee, and our CRC mentors who significantly helped us strengthen our proposal for this competition, and of course you for your attention. Thank you.
Great job, and thank you for the gratitude. I neglected to thank our organizing committee members, Duncan and Bea, who are here today. So thank you, organizing committee. And next up is KAIST.
Hello everyone, we are the MMMA carbon removal team at KAIST. I'm honored to have the opportunity to present our project at Carbon Unbound. It is a pleasure to introduce our DAC technology to you today, and I hope this presentation gives a clear overview of what we have built. KAIST is located in South Korea and stands one of the country leading institutions in science research. KAIST also operates the CO2 Management Center in partnership with Saudi Aramco and conducting joint research across the full CCUS spectrum. Building on this technology we will present today, our lab has also found startup M3I Labs, co-founded by Professor Dong-Young Go and Dr. Jinong Jung as alumnus of our lab. And Saudi Aramco holds the technical license as well. As we all know, that captures the CO2 directly from the atmosphere. To scale this up, there are a few challenges we need to address. First, handling a large air volume means the pressure drop must be kept low. The key here is shaping the powder sorbent into structural contactor like monolis or fiber. However, conventional fabrication of this structural contactor relies on sorbent, so which introduce indirect CO2 emission into process. This project set out to tackle both these challenges by proposing a new environmentally structured contactor and a new regeneration method. We aim to introduce a next generation DAC system with viable paths to net zero system.
The concept behind our contactor manufacturing was inspired by dry fabrication of battery electrodes. Conventional battery electrode manufacturing goes via a wet chemistry process, which involves the use of solvents. As you all know, the use of solvents adds not only process complexity and cost, but also increases the CO2 emissions of the overall process. This is why recently dry fabrication methods were developed, and this is why we also choose to adopt one of these methods to our sorbent manufacturing. Another big advantage of dry fabrication is that it allows for continuous production of the sorbent, and continuous production is necessary to bridge the gap between lab scale and large scale DAC deployment. We adopted the same philosophy to the regeneration step of our process. Rather than using conventional convective heating, we're using electrical energy directly via resistive heating, also called Joule heating. And because we're using electrical energy directly, we can also opt for renewable energy sources such as wind or solar without the need for any intermediate conversion. Achieving a net negative DAC process requires cutting the CO2 emissions in every step of the process, and the use of renewable energy is a necessary step into this direction. We combined both approaches, the dry fabrication and the Joule heating, into a single platform, which is our electrified film sorbent. The manufacturing of the sorbent is really simple. So we start with a solid sorbent in form of a powder and simply grinding it in a mixed mortar and pestle is enough to convert the sorbent into a dough-like mass. Roll pressing the dough yields a film of uniform thickness, and the final step is calendering this film onto electrically conductive substrate. And you can see how the direct manufacturing is possible in a continuous process. Furthermore, because the film is flexible, it is possible to bend it into many different shapes, which allows for direct modularization. In the example shown here, we rolled our film into a cylindrical geometry.
The electrified film solvent is loaded in a spiral wound configuration, and multiple films are connected in series. The thermal imaging data shows that the temperature across the sorbent layer is highly consistent. At 4 ampere, the sorbent reaches above the 110 Celsius in under 1 minute. This rapid heating response is the direct result of the Joule heating mechanism, and it is one of the most important features in our system for real deck operation. Furthermore, when comparing our system productivity with fiber deck system in the same model volume, our system have achieved a volumetric capacity of 73.5 kilograms CO2 per cubic meter per day, representing a 67% improvement. This shows that the dry fabrication approach not only offers a manufacturing advantage, but also delivers a meaningful gain in capture performance at the same time. To switch quickly from regeneration time to adsorption time, an effective cooling system is essential. The sorbent reaches high temperature during the regeneration time, so it must be brought back down rapidly before the next adsorption cycle can begin. To achieve this, we have designed a dedicated water flow channel integrated to the outer structure of the module. We carried out a CFD simulation for this water cooling system, and as the geometry shows, inner cylinder is a region where the sorbent is loaded, and while the water flow channel runs along the outer structure of the module. The result shows that this is significantly faster than the passive cooling alone, contributes directly to the reducing of the overall deck cycle time. And comparing to the air cooling and natural cooling and water cooling time, water cooling time has reduced up to 60%, which can contribute to increasement of the productivity of a single module.
Through this project, we've proposed a new structured contactor system along with a novel regeneration method. With a wind-based renewable energy scenario, the LCOC was calculated as $323 per ton CO2, demonstrating the practical possibility of direct renewable energy integration. That said, there are still some areas that needs to be discussed. First of all, as an amine-based sorbent system, material degradation and costs needs to be discussed. And also, we are planning to develop more concrete renewable energy scenario to provide more actionable guidance for the real-world implementation. Our roadmap through 2030 spans 2 tracks in parallel. Technically, we are scaling from the integrated bench-level cyclic prototype, which is capable of several kilograms per day by this year, to outdoor field pilot for tens of tons per year by 2028. and ultimately commission our first commercial plant to over 1,000 of tons per year by 2030. On the business side, we are building a clear path to below $150 per ton by this year, binding offtake agreements and project finances by 2028. And the end goal is the delivery of verified carbon credits to buyers in 5 years. Finally, we would like to express our sincere gratitude to our supervisor, Professor Dong-Hyun Ko, the Aramco KAIST Center, and the OpenAir team for their generous guidance and support throughout this research. We also would like to thank to our team members who contributed to this work. And if you got interested in our labs or projects, please visit us by the QR codes. That concludes our presentation, and thank you for your attention.
Great. So up next, we have University of Michigan with the Michigan Carbon Capture team.
All right, thank you everybody for coming out. Thank you for sticking around. We are Michigan Carbon Capture. We are a student project team made entirely up of undergraduates at the University of Michigan, and we are very excited to be talking to you all today about Project Sapphire. Project Sapphire is our urban wastewater project that hopes to do carbon mineralization and hydrogen production at scale with low power in our urban wastewater systems. So wastewater facilities in urban settings are a significant source of carbon emissions. In all our major cities, we are constantly producing tons and tons of organic waste, and every day these facilities are processing massive amounts of this sludge. And as it passes through these steps of processing, microbial colonies do the hard work of breaking down our organic waste into purer and simpler forms hard at work doing microbial respiration. The average wastewater facility will produce 47 million tons of carbon dioxide through this respiration every year. And that presents us with an opportunity. If we can capture this carbon dioxide at the source as it's being produced directly in these biological reactors, we can do significant carbon mineralization and significant carbon capture before it's released back into our atmosphere. Enter the diffusion-based microbial electrolytic carbon capture cell. I know it's a mouthful, but the MECC cell can integrate existing wastewater pipelines, building on top of that to limit the costs and risks associated with the new technology. It also produces clean fuel in the form of hydrogen gas and can mineralize carbon into calcium carbonate. Our main innovation here with this technology is this diffusion-based system. By moving away from previous expensive pump systems, we're able to limit the power and therefore enable greater scaling potential down the line. It's also low hazard by using microbes to assist our chemistries and takes advantage of a circular supply chain to utilize other industries' waste products such as RCA, crushed concrete. So now we'll walk through some of the biological, chemical, and mechanical aspects of our design.
Okay, so now to talk about the biological aspect of our project, which is our microbes. So we use the microbes in our system as a way to assist the electrolysis process. And in our system, in the bottom picture you can see, where we attach the microbes directly to our anode using cheesecloth. And we did so in order to maximize the amount of energy or electron transfer. And in our system, we chose to use a synthetic wastewater, so we didn't have to handle real wastewater. And it acts as a way to mimic the organic compounds that naturally occur in wastewater. And in the top picture, you can see this is a deactivated version of the sludge that naturally exists at the wastewater treatment plants. And at the wastewater treatment plants, the sludge acts as like a microenvironment with the microorganisms, and the composition depends on the time of year, the temperature, the amount of aeration and oxygen that the microbes are receiving. So each microenvironment is very different. And in the microenvironments, the bacteria form these colonies called flocks. And these flocks are held together. They're just like clumps of microbes, and they're held together by polymeric substances that are produced by the microbes, and they just work together jointly to maximize their efficiency in their metabolism. So the reason we chose to use microbes in our system is just because on all fronts it benefits us. So it helps us lower the amount of voltage that we need to provide to our system. As the microbes go through their metabolism, they produce electrons, and we use those electrons to overcome the thermodynamic threshold that is generated by the creation and formation of hydrogen gas in our system. And also the presence of the microbes allows us to avoid the formation of toxic gas compounds that include ions such as chlorine.
Okay, moving on to the chemical component of our system, the diagram you can see on the slide is the layout of our MECC system design. We selected a design where a single cathodic chamber is in between the two anodes. And so the single module of our system contains two active anode and cathode couples. And now I will walk through the flow of one of these couples to explain the chemical reactions. So starting with the anode, the microbes attached at the anode will break down organic matter such as acetate to release electrons and protons. And as Elena explained, these electrons create a natural electric potential, which significantly reduces the energy required for electrolysis. And the protons from the anode react with the calcium source to release calcium cations, which will be needed for carbon capture. This calcium source can be industrial byproducts or waste for waste reduction. For example, in our design, we chose to use crushed concrete. And now the cathodic chamber is where all the important reactions happen. The electrolysis at the cathode produces hydrogen gas. Research suggests that hydrogen from MECC is a clean, high-grade fuel, which can be collected in a gas bag for energy storage and use. And electrolysis at the cathode also produces hydroxide and therefore a local alkaline zone. The calcium cations produced at the anode will migrate through the cation exchange membrane, and once it hits the alkaline zone near the cathode, it will produce CaOH2. And this intermediate in presence of dissolved carbon dioxide from wastewater treatment transforms into calcium carbonate, or CaCO3. And as you may know, this is a highly insoluble mineral in water, so this precipitates out as solid, locking away carbon dioxide. The net reaction at the bottom is a summary of all the chemical reactions I just explained, but the main takeaway is that by integrating microbial activity with electrochemical hardware, we were able to design a system that produces hydrogen while also mineralizing carbon.
All right, so moving on to some of the mechanical requirements that our system needs. These requirements that our system needs will enable cost-effective carbon sequestration. So as my colleague Willow kind of talked about, we need to maintain a watertight seal within that inner cathodic chamber in order to keep the chemistry at the cathode and anode separate, as well as the electric potential. We need to work diffusively within a still water tank of wastewater in order to limit the cost of pumps. We also need to easily maintain our system to be able to replace our electrode material as necessary, as well as collect our calcium carbonate precipitate, which will arise within the cathodic chamber. And then, of course, we need to be scalable. So given all of these criteria, we landed on this design, as you guys can see. Just kind of at the bottom right corner, you can see a picture of one of our cells that we developed. These cells are attached to a 3D printed ring, which is then affixed inside of the chamber with a gasket, which will help create that watertight seal once that top part is bolted on. And so when we operate our proof of concept, it operates in sort of like a batch method, where we can only precipitate the carbon dioxide that is stored within the cathodic chamber. So once all that carbon dioxide has precipitated within the cathodic chamber, we would need to remove our system from the wastewater tank, open it up, remove the calcium carbonate precipitate, and then just wash, rinse, repeat. So as you guys can see, we performed a proof of concept trial in a lab setting and we were able to confirm that our system meets all the mechanical and operational requirements.
All right, but the million-dollar question, how does this scale? So that bucket you saw there, it sits, you can hold it in your hands, but the goal as we scale up is to do a first pilot test with a 10,000-liter container. This 10,000-liter container will look very similar, but will over 48 hours follow the process we just described. We're going to apply a 1 volt of power to do the electrolysis to produce our hydrogen gas. This comes at a negligible electric cost. And we also need 93 kilograms of RCA crushed concrete. Again, since we're sourcing this as industrial waste, it also comes at low cost. In terms of output, assuming an 80% efficiency, we expect to produce a kilogram of hydrogen gas and 80 kilograms of calcium carbonate. Now, this, over the course of a year, would sequester 6 metric tons of carbon dioxide. But is that all we can do? A 10,000-liter container is well below the capabilities of a wastewater treatment plant, especially an urban one. Our Ann Arbor wastewater plant at the University of Michigan can handle over 5,000 times that amount of water every single day. So as we scale up and go to higher and higher amounts, we might see up to 30,000 tons of CO2 in a year. And comparing this to existing systems, as we've mentioned before, this move to a diffusion-based system was our main change in this system because we're able to significantly limit the expenses, the operational expenses, which allows us to scale much further as we move along in the process. You can see here that a pump-based system, just through the necessities of creating larger and larger pumps that can handle massive amounts of water, will require increasingly large amounts of electricity to move all that around. And so our modular approach is able to keep costs low without compromising our yield. As we work towards the future, we're looking into ways to improve our efficiencies. We might try to include other flue gas from surrounding industries to help them limit their emissions as well. By inserting that directly into our cathodic chamber, we can further limit or we can further increase our yield. And by inducing a biofilm on our microbes, we can improve adhesion and therefore improve our hydrogen gas production. As we scale up, we'll want to test with real wastewater instead of the synthetic version, and we'll want to experiment with different geometries that can increase our diffusion area as much as possible, working towards the goal of eventually implementing in our own hometown's wastewater facility. So thank you so much for your attention. Thank you to our partners at Michigan, and of course to the OpenAir Carbon Removal Challenge. We'll be here afterwards for any questions. Thank you.
We now have Gigaton Bio from Cornell, Columbia, and Princeton.
How could these microbes possibly relate to removing gigatons of CO2 from the entire Earth's atmosphere? Well, I'm holding in my hand our Gigaton prototype, and this is, as we're speaking, taking critical elements from these mine tailings and bringing them into solution while sequestering CO2.
So why don't we already have a gigaton scale solution to the CO2 crisis? In our opinion, there are 4 major factors that are holding back all CO2 capture and sequestration technologies, that being speed, scale, permanence, and cost. And while there are tons of great innovations out there, the reason why we don't have one multi-billion CO2 sequestration technology is because at least one of these factors is missing. However, nature may already have an answer for us. Carbon mineralization already sequesters about 1 billion tons of CO2 per year through the natural breakdown of magnesium-rich ultramafic rocks, one of the most abundant rocks on Earth. However, this process still takes thousands of years and is far too slow to reach the rates that we need. So natural weathering, while it uses one of the most abundant rock substrates in the world, the speed of it is still too slow to match what we need. Enhanced weathering seeks to enhance this process through the acceleration through grinding and crushing. However, this introduces new scaling problems, such as land usage, energy usage through crushing, and also verification.
And our microbe can accelerate that process from decades to just days. We can permanently sequester CO2 with a gigaton scale potential. We can capture and sequester using ambient air in a single step. And we also use an abundant feedstock, the most abundant rock in the entire universe. And customers will actually pay us to use this because it's mine tailings. So we've made a breakthrough in the bioenhanced weathering space. This is our Gigaton Bio strain, and it takes these mine tailings and it releases the critical metals like nickel and cobalt into solution, and that's why you see it changing color. And then it also sequesters CO2 from the atmosphere. And we've also created a strain that is extremely high performance. As you can see, it's better than the natural process, it's better than the acids, and it's better than the normal microbe that you'd find in soil. It's actually our Gigaton Bio strain.
And relying on biology to improve that weathering process lets us actually address the biggest challenges of enhanced weathering that's typically done mechanically. So our solution has low land and energy use. Since it's being contained and highly controlled, we can precisely and easily measure the amount of CO2 we sequester. And finally, we can use any type of magnesium-rich rock feedstock that we want. So since we can use anything, why not use something that people want to get rid of and that's already above ground, such as mine tailings? You might not know this, but mines throw away around 80% of all the rock they process. It's not because it's useless, but because the ore grade is too low for them to process with their technology. These mine wastes get stockpiled into billion-ton heaps that mines need to babysit for decades, spending up to 30% of their revenue to upkeep. This is obviously a huge issue, but for us, it's a huge opportunity. We can use these tailings as feedstock for our process, and in that reaction, achieve a gigaton scale of CO2 sequestration. But that's not all. These tailings still contain critical metals like nickel, cobalt, platinum group elements that are very valuable and that we can refine through our process.
So how big is the opportunity really? We thought we'd show you. On the right-hand side of the screen is a typical tailing site at a typical mine. It looks like a mountain because it is. This represents decades worth of that bottom 80% of ore just sitting on a mine site discarded. Currently, mines are facing a huge issue. This is not only a big liability, but one of the real issues is that it's too costly and too difficult to extract the minerals within. At an average site that is compatible with our process lies $1 billion of untapped nickel and cobalt. Now let's get to the CO2. The reason why we're called Gigaton Bio is because we can use this abundant feedstock to scale. For every 2 tons of rock that we process, we can sequester 1 ton of CO2. And one of these sites is millions upon millions upon millions of tons. So if we're solving a core business problem for mines and really reflecting changes that will increase their bottom line, why haven't they thought of solutions? Well, the answer is that they're scrambling for solutions right now. We're actually in the midst of a new innovation wave. And on the screen here it represents a few of these initiatives. And if you've been here for the last 2 days, you may have noticed a serendipitous marriage between carbon capture, emissions abatement, and the mining industry. Gigaton Bio stands apart from this group because we can perform across all of these dimensions. We have a super engineerable microbe that can be improved in the lab in perpetuity. And truly, we are the only one of these companies that has the potential to make a mine a net carbon sink.
So coming back to those 4 major factors, we believe that our technology at Gigaton Bio addresses all 4 of them. As for speed, we're compressing a natural process from years to just hours or days. In terms of scale, we're using one of the most abundant rock feedstocks in the world, as well as one that customers will pay us to use. In terms of permanence, we have the gold standard in carbon capture in the form of mineralization. And most importantly, profitability. On day 1, we're able to extract critical metals like nickel and cobalt, which will be increasingly more important as the energy critical metals demand rises. As for our milestones in the future, right now we're scaling out of the lab, looking to partner with mines and start doing a pilot in the next year. And then from there, we'd want to do a full-scale deployment at a mine site, capturing gigatons of CO2 as well as critical metals. Right now, our technology works great in the lab, and what we're trying to do is integrate real-world tailings into our fully developed process. We've received about 100 pounds of mine tailings already, and right now we're working on developing that full process using that test material. So why are we the right team to execute on this? We're a team of diverse experts in bioengineering, climate finance, and geochemistry, and we've worked together on this project for years, developing this biomining process together in the lab, as well as traveling across the United States, visiting several mine sites and interviewing potential mine operators. And we'd also like to give a big shout out to our advisors, Buzz and Esteban, who are here. And thank you so much to OpenAir and Carbon Unbound as well. As for our asks, right now we're in an intense customer discovery phase, looking to speak to mine experts and mine operators that we'd want to partner with. We're trying to understand how we can solve a real problem for them today. Also, if you're an early stage investor and you're interested, we'd love to talk to you. We can give you our business card. Thank you very much. We're at Gigaton Bio.
Hello. All right, so that was our program. Thank you to everyone for sticking with us and supporting the students. If you have any questions, please feel free to come up and talk to the students and give them one more round of applause. Thank you.